Okay, so good morning. Thank you for the invitation. So first of all, happy Valentine. So I will talk about fluctuations. So at the beginning, I wanted to give a talk with details on the analysis, and after the session of yesterday, I realized that it would be nice to have more of an overview of what we can say about quantitative estimate in stochastic homogenization, and not necessarily only about fluctuations. So I will, instead of presenting analytical details, I will essentially give you a short overview of what we can do. So first of all, this is joint works with Mitya Duerinckx from Brussels, Stefan Neukam and Felix Otto. And there are also related works by Peter Bella, Julian Fischer, who will speak on Thursday, Ariana Giunti, Ben Ferman, etc. And I have to say also that it's related and partially inspired by works by Jim Nolan, Scott Armstrong, Charlie Mark, Jean-Christophe Murat, Tomokushi, and Yugu. Okay, so just to fix notation, what is stochastic homogenization? For me, you consider A epsilon, which is the epsilon rescaling on some field A, a matrix field, say diffusion coefficients, which are coercive, stationary, and ergodic. So in particular, I will never discuss in this talk anything related to high contrast problems. So for me, say that A will be bounded between 1 and 2 or 1 and something, but the something will be fixed. It will not be high. And so what I'm considering is this standard elliptic equation, say with Dirichlet boundary condition and a domain D. And so I'm interested in the solution of this, which is a family parameterized by epsilon, and on top of this, it's a random solution, because A is random. Then homogenization theory tells you that at the limit when epsilon goes to 0, you can describe U epsilon by the solution of a similar equation, but with constant coefficient. On top of this, they are deterministic. And U naught describes U epsilon in some weak norm. So U epsilon weakly converges to U naught almost surely in H1, and you also have convergence of the flux weakly. And this homogenized coefficient is essentially as in the periodic case. So it's an average of the original coefficient times some kind of what I would call a measure, which is just E plus the gradient of the corrector. So you take a kind of weighted average of your original coefficient. In the periodic setting, these brackets would simply be the periodic average. And in the random case, it's an expectation. But in all the talk, if you don't like expectation, you should just interpret this as the average on the periodic cell, except that the periodic cell is now an infinite dimensional space. Okay, so that's the notation, the setting. And what I'm interested in is the speed of convergence in this. So this is the ugliest slide I have, so don't be worried for the rest of the talk. So I just want to give you the state of the art a few years ago. So things that started in Bonn, actually, 9 years ago. I didn't think it would keep me busy for 9 years, but it does. So essentially, what we did at the beginning was to consider a discrete elliptic equation. So before, I just used a continuum elliptic equation, the usual thing. And actually, what we did first is look at a finite difference scheme, if you like. So this is on a grid ZD that we rescale by epsilon. This is the forward, the forward gradient, the backward divergence. A epsilon is just a diagonal matrix. So if you think of a square lattice, that's the conductivity of each edge. And I assume that the conductivities are IID, between 1 and 2, say. And so they are independent from one another. So that's distributed according to the IID measure, if you like. And so you can also prove the same kind of convergence, the fact that U epsilon converges to U naught, solution of the same equation. This time there's some kind of discrete continuum limit at the same time. So it's a continuum equation. And U naught describes U epsilon at the limit when epsilon is small, almost surely. You also have a corrector equation, which is essentially the same as in the continuum, except that you have finite differences. And so what we proved is, first, that the gradient of the corrector has all its finite moments bounded. If you think a little bit, the only thing that the equation gives you for free is the result for Q equals 2. That's an energy estimate. To have something more than Q requires some work, and that's not trivial because essentially it would in the spirit, it's like a maximal regularity for the Laplacian. But it's not the Laplacian. We have heterogeneous coefficients. So you know that if you want to apply Calderon-Zingmuth stuff, it does not work. So essentially, the only thing you have a priori is Meyers. You are slightly more integrable than you think, a bit more than 2. Here it's Q. I mean, it's huge. So that's a huge gap between what is known deterministically and the fact that you take expectations there. More interestingly, the bounds on the corrector. The bound on the corrector is essentially what you need to control anything you want to compute, right? And so we have a dichotomy here. So essentially all the moments of the corrector scale the same. So here there's a dependence of Q in the estimate. So when I write this, it means up to some constant, which only depends on, here it's Q and dimension. And so in dimension larger than 2, the corrector is essentially bounded. And in dimension 2, it grows logarithmically to a factor of 1/2. So if you use these bounds, then what you can prove is that the error in the 2-scale expansion, so that's what I want to estimate. This is the homogenized guy, minus the correction due to the corrector. This is the notation for the corrector vector in all dimensions. And so if I were in the periodic setting, I would get epsilon. I'm on a torus, so there's no boundary layer, right? And here, what the analysis tells you is that you have epsilon in dimension larger than 2, and you have epsilon times a log in dimension 2. And all this started actually not for this thing, we got that much later. Everything started from numerical analysis point of view. So what we wanted to understand is, what can we say about the approximation by periodization? Namely, you take a box, a cube, you don't know the boundary conditions you have to impose. You know that Dirichlet is not that good, so use periodic. That's nice because IID combines well with periodic boundary condition. So you take periodic boundary condition on your big box. You compute the corrector with this periodic boundary condition. You take an approximation by taking just the average of this guy with the periodic corrector. And instead of taking the expectation, you take the average on the big cube. This defines this approximation AL. This is a random quantity. And you want to understand how close this is to what you want to compute, the homogeneous coefficient. Well, first, what we prove is that if you take the expectation of what you compute, then that's close to what you want to compute, up to this error, which is very small. If you took Dirichlet boundary condition, you would get L to the minus 1. Here you have L to the minus D times the log correction. And then you can ask yourself, and here comes the fluctuations, what are the fluctuations of your AL? So you compute something which is random, and we would like to know how does it fluctuate. And the answer is that actually it fluctuates like a normal random variable. So this is just for normal random variable. Forget about this distance for now. What this tells you is that what you compute minus what you want to compute essentially scales like L to the minus D over 2. So it's like a central limit theorem. So this is a central limit theorem for AL, what you compute. So AL minus the limit scales like a normal times L to the minus 2D. And if you want to know, this is the Wasserstein-1 distance. So that's just a distance between probability measures. And on top of this, you have a rate. It fluctuates at L to the minus D over 2 up to an error, which is L to the minus D, because that's L minus D over 2 times L minus D over 2. So that's L to the minus D. And then there were other works. So this is all of this with Felix Otto and Stefan Neukamp. This is with Jim Nolan. And then you can also understand what is the limit of the corrector. This is what Jean-Christophe Moura and Felix Otto did. And this is Jean-Christophe Moura and Yugu, but I will come to that later on. Okay, so what's the aim on the outline of my talk? First, I'd like to treat the continuum setting and not the discrete setting, because what it's interesting in practice is the continuum setting, right? And I don't want to deal only with scalar equations, because this was a scalar equation. We used the maximum principle in the proofs, and even the De Giorgi-Nash-Moser theory. And now I'd like to also treat systems, for which I don't have all this regularity theory. So that's the first goal. The second goal is I do not want to focus only on IID problems. Why? Because in the pictures you've seen yesterday, everyone who has shown pictures of a random field, there were correlations. Just think a moment, there was these balls, inclusions. The inclusions never overlapped in the pictures I've checked yesterday. Right? In all we've seen, there was never an overlapping, which means that the field must be correlated. Otherwise, there would be some overlap. So there are correlations. And not only this, I like to treat most of the examples I could see on pictures. That's one of the other goals. And then, that was the original aim of my talk, develop a unified theory of fluctuations. So there will be 3 parts in the talk. First, a part named weighted functional inequalities, which is just the translation of that. What can we say about practical examples? The second part will be to derive quantitative estimates under this assumption. And the third part will be about fluctuation. So as I said, ellipticity ratio will be fixed over the 1. So no high contrast. So let's start with weighted functional inequalities. Okay. So first, what is it and why is it useful? So what a functional inequality? So for me, that's a functional inequality in probability. And essentially, it is a Poincaré inequality, but in infinite dimension. So Poincaré inequality, you know what it is, right? You're on a torus in dimension d. Then you bound the L2 norm the L2 norm of a function minus its average by the L2 norm of the gradient of the function. And then there's a constant in Poincaré's inequality, and its k is essentially like the largest distance in the diameter of the set, right? Okay. Here the problem is that I'm in infinite dimension, because in the probability space, if you think of IID coefficient, I have a countable set of variables. And so the functional inequality here essentially is this Poincaré, the usual Poincaré function inequality in infinite dimension space, and so you have to cook up a nice derivative. So all the questions boils down to finding a nice derivative. So more precisely, I'm considering a function f of A. A is a coefficient field. If you think a little bit, if you solve a PDE, minus div A grad u equals f, u is a function of A. So usually you see it as a function of f, right? Or of the boundary value. But it's also a function of the coefficient. So that's, in this spirit, I want to use this kind of inequality. So f is a function of the coefficient. And I take a coefficient which is a random field, and which is distributed according to some probability measure. So the example I've gave you 5 minutes ago is the IID case. So if you're in the discrete setting, you have this IID coefficients. So that's the law. That's the distribution, IID coefficients. So think of a random checkerboard, if you like, in the continuum setting. Then a standard spectral gap would be like this. You control the L2 norm of f minus its expectation. So that's really like the left-hand side of the usual Poincaré inequality. The L2 norm of u minus its expectation, except that now the L2 norm is the L2 in probability. What do I have in the right-hand side? I have some kind of gradient to the square expectation. So this is essentially some kind of L2 norm of a gradient of f. The gradient is, however, taken in terms of the coefficient field. And how do I take it? I take an average over whole space of the derivative of f with respect to A on a cube centered at x. So if you like, you split your space into unit cubes, and you look how much f depends on the coefficient on that region. So this notation for derivative can be anything. Not completely anything, but it's essentially a measure on how much f depends on A on that box. Okay, so that's like a derivative, but it's okay. There are a lot of possibilities, and I won't give any details on that. So why is it an interesting inequality? Because it allows you to control moments of some function f, which is nonlinear function of A, using the gradient of f respect to A. Okay, so why is it useful? As I told you, if you look at homogenization, if you want to understand fluctuations, what is the input? The input is how A epsilon fluctuates, and what's the output is how U epsilon fluctuates. So you want to understand how fluctuation of A are transmitted to U. So you want to understand the map, which to A maps U epsilon. And this is typically the kind of inequality you will need. How much does U epsilon depends on A, like that. Okay, so that's why it's an interesting tool to study quantitative things in homogenization. Okay, so what type? So actually you can deal with everything. It's just you have to cook up the right. So you can take discrete or continuum stationarity. I prefer discrete continuum stationarity. I don't know why. I will stick to that because Poisson is continuous. Okay, so there are three typical examples which satisfy these inequalities. The first one is Gaussian coefficient with integrable covariance. So of course, the Gaussian coefficient is not bounded from below nor from above. So what you take is typically a Lipschitz bounded function of. But if it's local, that's fine. So take arctangent of your coefficient, if you like. Random inclusion with bounded radii centered at points of a Poisson point process. So take a Poisson point process, and each time you have a point, you put a random inclusion. You put a spherical inclusion of radius 1. Okay, so they can overlap because Poisson point process overlaps, right? That's the typical examples. If you take unbounded radii, nothing, or Gibbs measures with well-behaved Hamiltonian. Okay, comments. What about non-integrable covariance? What about unbounded radii? What about non-overlapping inclusions? And this, how do you that's something from statistical physics. Have you ever seen some coefficient field given by the Gibbs measure associated to Hamiltonian? I've never seen that. So that's not so useful. So in some sense, this is a bit restrictive. And you cannot deal with all the nice pictures we have seen yesterday. Well, so this is, so I don't know about the copyrights here. That's Google, right? So, so I just wanted to show you the typical examples we've seen yesterday, you see all the time. Typically overlapping, so this is Poisson point process, the one for which we have the standard functional inequality. This would be this Gaussian field with some kind of thresholding on top of this. This would be Poisson point process, Voronoi tessellation. And then each time you have a Voronoi cell, you pick at random what's the color. Here would be the same with the Delaunay tessellation. Okay, by the way, neither of them satisfies standard Poincare inequality. Another example, that's non-overlapping inclusions with random radii. We've seen that yesterday as well. This is typical inclusions, which could be centered at random point process, at point of a random point process, Poisson point process. The thing is that you see that the orientations are correlated. So there is correlation in there. And okay, so essentially what I wanted to do is treat all the examples I could find in that book. I mean, you have to start from something. So that's what we essentially did. And so how did we do that? So first of all, what is the common point, the common feature of all these examples? Well, all these examples are constructed by hands. So what do I mean? They are constructed by hands. Essentially, A, the coefficient field, is some map of some B, where B is a typically higher dimensional random field, which has a product structure. If you think of Poisson point process, okay, that's the same. So Poisson point, so I will give two examples. So let's keep it like that. So B is a higher dimensional random field, which satisfies some spectral gap inequality. And H is a non-local, potentially random projection. So essentially, you have something in a high dimensional space, which is simple to describe. You project it on a lower dimensional space, and then it becomes a bit complicated. So first of all, remark, this is very common in math. Think of quasi-periodic function. What is a quasi-periodic function? That's a periodic function in high dimension that you project using a winding matrix. So you restrict the dimension, and you get something very complicated. This is not periodic, but it has some nice structure. It had averages. But that's complicated. And the simple description is you go back to the higher dimensional space, and it becomes periodic. So that's a bit the same picture here. And now, f of A can be written as f, I don't know the word in English, composed with h of B. And for that one, you have a spectral gap with respect to B, and you want to have a spectral gap with respect to A. So essentially, you have to make a chain rule, because I want to differentiate one with respect to the other. So you want to apply a chain rule. The problem is that you are in infinite dimension, and you only have a white sense derivative. That's not a local derivative, so there's no chain rule, actually. So you have to deal with that problem. Two examples, the Gaussian. A is your Lipschitz function, to make it bounded from above and below, of what? Of some convolution kernel convoluting with a Gaussian white noise. That's how you construct a Gaussian field, right? The Gaussian white noise satisfies spectral gap. Okay. Be careful because of measurability, but whatever. It satisfies spectral gap, and so you want to understand how this satisfies, what kind of spectral gap this satisfies. Other example, Poisson inclusions, this time with random radii. So each time you have a point, you pick a random radius, according to some law, can be unbounded. And so you define your A as alpha where I have no inclusions, beta where I have an inclusion, and where do I have an inclusion? The union of the balls center at xi and of radius ri. So these are two examples of this. And so what you can prove now is the following kind of weighted functional inequality. So remember, before I didn't have this integral over L, I didn't have these things, and L was 1. Now what I'm saying is that if I have correlations, essentially what I have to, so the intuition behind that is, since fields are correlated, maybe you have to take the derivative on large sets. So you have to consider the fact that things are correlated far away, so you have to see the correlation, which means that in some sense, you have to compute the derivative with respect to very large sets. But this is something which does not happen that much. You don't need to do that often, because the probability is small. So essentially, how you should interpret this inequality, this is what you have. You have to see all the points. This is normal. You have to understand how much the random variable depends on your coefficient field at all the points. But then you have to consider very large sets around each point. But the larger the set, the less it's important. And the less is important, it's encoded in this function pi, which is some kind of a weight. So if you take L to be very, very large, then you will put a weight PL, which is very, very small. So these things happen, but not too much. And so this is, in some sense, the weighted version of functional inequality. And in the two examples I showed you, then actually this holds true. For the Gaussian, the pi is the derivative of the covariance. So that's a covariance function of your Gaussian field. That's a convolution of gamma with itself. I assume that it's less than little gamma, which is some Lipschitz function. Then the weight here is given by minus gamma prime, the positive part. And for the Poisson random inclusion, it's even simpler. The pi is just the probability that the radius is between L and L plus 1. So in all the examples, you can actually pretty easily compute the pi, and this is true. And so there's a crucial concept. I don't have time to enter into the details, but there's the concept of action radius, which is essentially the fact that measures that's a random variable which measures how much you have to go to see independence. Okay, so what's the intuition about this functional inequality? So how do we use them? So first, there's the first version with the variance. There's also a version with the entropy or with the covariance, depending on what you want to do. And so there are two properties. First of all, concentration of measure phenomena. So that's a big word, just to say that using this kind of inequality, you can bound high moments of your random variable. Why is it important to bound high moments? Well, if you think of the corrector is a quantity which is not bounded in stochastic homogenization. It is not bounded, but it has a lot of moments. So if you have a lot, that's the same difference between a function which is in LP for a large P and a function which is in L2. It cannot explode the same way locally. So that's a nice information you want to know. So this is the information it gives. And actually, using this in a nice way, you can prove even stretched exponential moments. I will come to that later. And then this is essentially related to the fact whether you have entropy or variance on the left-hand side. And then here, the pi is a measure of correlations. And you can really relate the pi to the correlations of your random field. And so in some sense, the pi will be the driving quantity for the estimates on the growth of the corrector. So this will give you the stochastic integrability, or the moment bounds. So all the moment bounds will be the same, and what will be the scaling, it will be given by pi. I will come to that later. So essentially, if your field is very, very correlated, the corrector will grow sublinearly, of course, because it's the consequence of ergodicity, but it will be algebraically growing and as fast as you wish under the threshold 1. Okay, so let's be a bit more precise about that. So the driving quantity in homogenization is the corrector. Well, actually, it's not the usual corrector only. So what we understood some years ago is that, so you know, by H convergence, essentially what you have for non-symmetric coefficients is that in order to prove homogenization, you need two things. First, convergence of the field. Grad U epsilon converges weakly to grad U home, but also convergence of the flux. The flux is not a direct the convergence of the flux is not a consequence of the convergence of the field if you have non-symmetric coefficients. So essentially, you have to assume as well that the flux converges weakly. A epsilon grad U epsilon converges weakly to A home grad U 0, right? Which tends to say that, okay, the phi is the usual quantity that corrects the field, but you might as well consider, with equal importance, something which corrects the flux. And the field which corrects the flux, it's the flux corrector, which I call sigma. And sigma in direction EI is a matrix field. So the usual corrector is a scalar field. This is a matrix field, which is defined like that. The Laplacian of sigma I is the curl of the flux. So this is the flux minus its expectation, if you like. So I don't have time to enter into detail, but you see from this formula that this matrix is Q-symmetric because of the curl you take. And more importantly, it satisfies divergence of sigma I equals Qi. And that's important because most of the time you have this term on the right-hand side when you try to make an estimate. And if you don't see that in the divergence form, you lose an epsilon in the estimate. So this is something which is needed to turn the local error into divergence form. And so what you have for free by ergodicity is that the second moment of the gradient is bounded. But we want more. So quantitative results. So there are three questions. What are the moments? So essentially, what are the moments of gradient phi? What can we expect in terms of scaling? So you know that the expectation of grad phi is 0 because it's a gradient. So it's like the average of a gradient is 0 on periodic set on a torus. That's the same here. If you take local averages of the grad phi, they must converge by the ergodic theorem to 0, and you want to quantify this. So I take grad phi, I take averages on a big ball, and I want to see how fast it goes to 0. And last question, what is the growth of the corrector in X? So I know that in the IID case, in dimension larger than 2, it's essentially bounded. Okay. Expectation, every moment is bounded. So what's about the correlated case? So now I will specifically treat a Gaussian field whose covariance matrix is bounded, a covariance function is bounded by a power decay, beta strictly positive. If beta is larger than 2, I have integrable correlations. Otherwise, it's not integrable. And I would say it has a heavy tail. Okay? So that's the typical coefficient field I will consider. Then I recall in this case, I have my functional inequality with this weight. And actually, the rule of the sum to understand scalings in homogenization is the following. You can say pretty fairly that averages of grad phi behave like averages of the coefficient. That's the rule of the sum. If, so for instance, if I take averages, spatial averages of the coefficient field, and I apply this estimate, then a direct computation gives me that the variance of this So I just take, it's easy, that's just an average of coins, if you like. You toss coins, head or tails, you count the number, I have R to the D realization in there, and I want to see the variance. If I have IID coins, the variance will be R to the minus D. Well, that's true. If I have integrable correlations, this is actually R to the minus D. But if I'm just borderline beta equals D, then I have a logarithmic correction. And if you have a heavy tail, then you don't have the CLT scaling anymore. You see the tail here, that's minus beta. So no CLT scaling for beta, less than D. Okay, so that's the best you can hope, because that's what's true for linear for the coefficient itself. And actually, what we'll prove is that it's also true for the gradient of the corrector. So moment estimates, so first of all, this pi star, which is defined like this, okay, and depending only on beta, drives the stochastic integrability, so that's not so important here. Here is more important. The average of the corrector on a ball of size r scales like p star to the minus 1/2. So if you have integrable correlation, it means CLT scaling. Up to some random variable here, which has nice moments, so you can forget about it. And you have all these choices for the rest, for the heavy tails, for instance. And for the growth of the corrector, well, that's a bit more complicated than for the discrete setting, because I have correlations now. If I have integrable, so here this is subtle. So essentially what drives the growth is beta over D. If beta over D is larger than 1, then it's fine, otherwise it's like that. Okay? Right. So now you can apply this to prove two-scale expansion. So I don't want boundary layers, so I'm on the whole space. I'm solving the equation RD. I take essentially a localized right-hand side. I'm solving the equation, and I want to know how close the gradient of the solution is to the two-scale expansion. And actually, it's close, depending on the growth of the correctors, so depending on the beta. And you see that it can be arbitrarily slow if beta is small. And you can do a numerical analysis of a numerical method for correlated field using these kind of things. And I think that's the only way I know we can use it. Okay, so last part of the talk, unless you have questions, is about fluctuations. So there are three quantities I'm mainly interested in. So first of all, yes, let me say that I will again consider a Gaussian field with this beta for the correlations, for the covariance, the decay of the covariance. And so I am interested in this, the solution of this problem. And I want to understand the fluctuation U epsilon. So typically what I consider is, so fluctuation, there is no hope to catch the strong fluctuations of U epsilon, because it only converges. I mean, the strong fluctuations will be of order epsilon square, and so you have no CLT scaling. So you cannot really look at U in a strong norm, so you have to look at U in a weak norm. So what is a weak norm? You take a test function, you multiply your function by this test function, and you integrate. So this is a weak norm. If you understand the map, which maps G to this, then that's a characterization of fluctuations of U epsilon. So you look at how much U epsilon deviates from its expectation. You multiply by G, you integrate. So that's something I like to understand. And then it's more of a theoretical interest. That's the fluctuation of the field of the corrector. So I take a map F, and I test it against a home grad phi, and I want to understand how it scales or to what it converges, and the same for the flux. So these are three quantities, three functionals. So the first question before asking whether it will converge to some law, well, it's what about the variance? How does it scale? First question. Then, are these quantities related? Okay. And the third thing, what is their asymptotic law, if any? Okay, so what are the natural scaling? So remind you the pi star. Weak fluctuations. Essentially, what you have is like the CLT scaling if you had integrable correlations. So the natural way to rescale this I is to take the CLT scaling, or the associated scaling with beta. So the same as for the average of the coefficients. And then the variance becomes 1. And that's the same for the three quantities. So actually, you have, this is the correct quantity to look at, rescaled by this power of epsilon. They are here. Right. So actually, to understand the relationship between these three quantities, there's a missing quantity. And actually, the driving quantity, and that's I think the main message of my talk, is this quantity, which we've called the homogenization commutator. So this is the flux of the corrector minus Heom times the field of the corrector. So let me first try to convince you that it's a natural quantity to consider. So it's definitely natural for someone from mechanics. Why? Because homogenization, what is it? At the end of the day, homogenization is just the art of averaging fields and fluxes, right? You average a field, you average a flux, and you say that the homogeneous coefficient is the thing which turns your field into a flux when you multiply by it. So this is what I've tried to explain here. At the macroscopic scale, where you have the true law, the law of your coefficient, the flux is A times the field. Okay, that's the definition of the flux, if you like. At the macroscopic scale, the flux is the homogenized coefficient times the field. If you look at the difference, microflux minus macroflux applied to this corrector, essentially this is a measure of the accuracy of homogenization. Were you right to replace A by Aom? Well, you're right in the limit, but are you right at epsilon fixed? Or here I would say at a large scale? Then this is a nice measure of this problem. So that's kind of a defect in the homogenization limit. And in some sense, this is a quantification of the defect in Hill's lemma in mechanics, you could say. Okay, so this is a typo. Well, so why not consider now the same functional for this homogenization commutator? So the homogenization commutator is a natural quantity. Let's look at these weak fluctuations. Actually, when you look at its scaling, that's again the same. So now I've scaled it so that the variance is 1. And here comes the main result. So consider F and G which are smooth and compactly supported in the whole space. You're again interested in the solution. I didn't write it down. You're again looking at this. And you want to understand the fluctuation of U epsilon. That was the aim of the I1. df is here, dg is what you're testing with. Remember, so that's U epsilon minus its average times g times the correct rescaling. And this is a function of f. So which means that this I is a function of f and g. Then you consider two other quantities. Or there should be bars. U bar, which is the solution of the homogenized problem for f, and V bar, bar is missing, which is the solution of the adjoint homogenized problem with right-hand side g. So I have f, I have g, and I have two homogenized solutions. Then what I claim is that the fluctuations of U epsilon are described by the fluctuations of the homogenization commutator tested at this matrix field, grad U bar, grad V bar. And why do I claim that this is a nice characterization of the fluctuations? That's because on the right-hand side, I have some random variable here, which only depends on U bar and V bar. on actually high norms of this U bar and V bar, but whatever, I've assumed they are smooth, times essentially something which depends on beta, but which is small with respect to epsilon to some power. So since this has a variance of order 1, this is small with respect to that, which means that at leading order, the fluctuation of this are given by the fluctuations of that. Even if you don't know what the fluctuation of this is, it gives you the information that whatever happens, if this fluctuates, this fluctuates the same way. So you have characterized the fluctuations of the solution. And for the other two quantities, actually, that's just some algebra. So I don't want to enter the details. So the main message is really, this describes the fluctuations of your solution. And so the only quantity you have to consider is this homogenization commutator. All the fluctuations of your solution operator are encoded in the fluctuations of the homogenization commutator. Okay, so can we say more? Can we say something about the limiting law of this homogenization commutator? Now that you've understood that all the fluctuations are encoded by this quantity, you may as well want to understand that quantity more in detail, right? So there are two types of results and two cases. The first type of result is approximate normality. So does this I epsilon naught, so does this average of the commutator behaves like a normal random variable for small epsilon? That's what I call normal approximation. And then the second quantity, to turn this normal approximation into some CLT, you have to understand whether the variance has a limit. And so that's the second question. So for the first question, actually, we have a result for all betas, but then there's a dichotomy when it comes to the second question. The second question, for the second question, the answer depends whether you have integrable or non-integrable correlation. So let me start with approximate normality. So essentially, this is a result which is based on Chatterjee's second-order Poincaré inequality, which is related to the Stein method, but applied now to these Gaussian fields with heavy tails. And so what we've proved is that in total variation, the distance between the quantity you want to understand and its variance, so the I epsilon over the square root of its variance, you want to compare it to a random normal variable, so they're just a Gaussian. You want to compare it, and well, actually, this is small, and how is it small? It's related to this pi star again. So you have that this is small. So essentially, this behaves like a normal random variable with some variance with this variance. Beta is the correlation. That's the decay of the correlation. Yeah. So if beta white noise would be beta equals 0. So here that's a mistake. I should have had beta. Sorry, here there's no d. It should be beta over 2. The less beta is, the slower it decays. Right, then convergence of the variance, I told you there were two different settings. So either beta is larger than d, which means that you have integrable correlation. So what you should expect is a true CLT. And that's what you get. Essentially, there exists a fourth-order tensor Q. And very importantly, that fourth-order tensor Q can be approximated exactly as you would approximate homogenized coefficient. Actually, you don't need even more quantities. If you have enough to compute to approximate the homogenized coefficient, you have enough to approximate this matrix Q, this tensor field. And so the variance is asymptotically given by the average of F with this Q. So that's just quadratic form. So you have a complete description. And if beta is less than d, so it's non-integrable, then my conjecture is that there exist two tensors, Q1, Q2, and actually the thing is that here you have a fractional Laplacian, essentially here. And that's not a conjecture in dimension 1. It was proved by Guillaume Ball and collaborators. But in higher dimension, we have some ideas, but the proof is not complete yet. So there's okay, and this holds without any extraction. So all the sequence converges. here, not all the sequence converges actually. So there could be several limits. So the limiting law does not exist actually. You have some compactness, but it's only because of Gaussianity. Right, so conclusion for integrable correlations, well, you have everything. You know that this fluctuates like a normal random variable with this variance, which you can compute. So you know all the fluctuations of your solution. And a bit of caution, the two-scale expansion of U epsilon does not fluctuate the same way. So actually, if you use the two-scale expansion to approximate fluctuations, you're wrong. And that's something that has been proved. The fluctuations are not the same. So what about numerical approximation? So in dimension 1, there are works by Guillaume Ball as well. Okay, so that's the reference. But before I still have 4 minutes. I have 2 questions for the audience. So related to the talks I've seen yesterday, and conversation with Frédéric, for instance. So I have 2 questions. The first is about oversampling. So let me tell you what I can prove about oversampling and what I've looked at answers in the literature and I didn't find any. So take A, which is a periodic field. Okay. You approximate the corrector by the solution of the corrector equation on a simplex of size h plus delta h with Dirichlet boundary condition. And then you're just looking at the corrector inside the simplex. So that's the usual oversampling stuff. So you have your simplex. This is delta h. And this is h. Okay? And so you're just looking inside. And you put the boundary conditions outside. And so yesterday what I could prove is this. That if I compare phi epsilon. So why did I put phi epsilon? So there's no, yes, that's epsilon. So I want to compare grad phi epsilon to grad phi epsilon with the zero boundary condition on the boundary of the simplex, the larger simplex, and I want to compare it inside, in the small simplex. And so what I could prove is h to the d, that's normal, that's the volume of the simplex, it should be there. Then I have epsilon square, that's a norm to the square, so it's compatible, right? But what I have on the denominator is h delta h. Whereas what I thought, or usually people take only a small number of layers in terms of epsilon, say n layers. So instead of delta h, take n epsilon. And what you would think is that you get something like that. Not this delta h, because delta h would not be good. It would be just 1 over n, whereas I want epsilon over h. And so my question is, do you believe in this second estimate? Don't need an answer now, but just do you believe in this? That's my question. And then the second question is, now that you've seen my new lubie, which is just correlated Gaussian fields, if you consider A, your matrix field to be the arctangent of a Gaussian field plus 2, so that it's really nicely bounded from above and below, where B is a scalar Gaussian field with some covariance function which decay very slowly. So my question is, has anyone already used their favorite numerical homogenization method to solve this problem? It's just the simplest you can think of. You're in 2D, you're solving this with 1 as a right-hand side and 0 as boundary condition. What is epsilon? A? Epsilon. That's a small, that's the usual. X over epsilon? Yeah, that's sorry. Yeah, so A epsilon is your coefficient field rescale. So epsilon is small. Okay, and so what I can prove is so first, has anyone tried that? Does it make sense? And second question, okay, when I try to make the numerical analysis of methods like that, then the only thing I can do is say for interior estimate, because as I told you, I'm afraid of boundary layers, so I'm always place myself away from boundary layers. And so the difference between the solution minus the approximation with capital H, little h, and this epsilon in H1, the only way I can do that is to use the triangle inequality. I compare U epsilon to the two-scale expansion. I compare the two-scale expansion to what I compute. right? That's the only way I know how to make this numerical analysis. Okay, use my bounds. What do I get? I get epsilon beta over d, two-scale expansion. I have h and h because this field is nicely Lipschitz. And then if you use my this little stuff here, what I get is epsilon over h beta over d times h over delta h 1/2. And what I call that is Lowy-Slowerson, because if beta is very small, this does not converge very fast. And so my question is, do you believe this is sharp? Okay. Or would you have numerical experiment which would show it's not sharp? Okay. Okay, so I think I'm done with the question, so I can go back to the references. So for weighted functional inequalities, that's something I did with my PhD student, and it's almost online. Then the quantitative estimates are based on the big work, which we split into two versions, the regularity theory on the one hand and quantitative estimate on the other hand. Then the pathwise theory of fluctuation is a joint work with a PhD student and Felix Otto. And then we have nice work with Felix on the corrector and stochastic homogenization, but that's more refinement of these things. And then there's nothing I didn't speak about, but which I think is very interesting. It's a long time behavior in homogenization. So you take the wave equation and you want to reach times which are of the order of epsilon minus 1, 2, 3, 4. And what happens? And then that's really challenging. Okay, so I think I'm done, and I thank you for your attention.
Any other questions? So the commutator, is it it's there's only one such commutator? Is that what you're claiming or no?
Yes, there's only one such commutator. So they are, okay, so when I was talking about credits at the beginning of the talk,
this is probably what the residual estimate.
not completely, no, this is not completely that. It looks like this, but I paid attention yesterday and it was not this, because your thing goes to 0 in a strong norm, whereas this goes to 0 weakly. That was my question yesterday, actually. So there's only one homogenization commutator. The thing is that, so there are this series of work by Scott Armstrong, Jean-Christophe Moura, and Tomo Kushi, who essentially establish also sharp convergence rates in homogenization. Their assumptions are somehow different. They assume finite range of dependence of the coefficient. So you're in the case where you have few correlations. The only catch here is that they don't have necessarily a point carré or a functional inequality, because that's a mystery, but yeah, coefficients with finite range of dependence do not necessarily satisfy a functional inequality, so they had to do differently. And actually, we did also that at the same time with Felix. We're using another method, and in their method, they are based on some variational version. Yeah, so their proof is very variational, and they introduce some quantities, and actually one of their key quantities, it's not easy to see, but I called it the homogenization commutator in disguise, in variational disguise, because actually at first order it looked like that. So actually they also get some convergence to white noise and things like that, using another quantity, which is at first order, but you see that at the end of the proof only. At the first order it's like this. So essentially it appears also in other works, with another name and another form. What I like here is that it does not depend on the fact that A is symmetric or not, whereas if you use a variational method, you have to embed your non-symmetric problem into a symmetric problem. And also it's very intrinsic because it's only based on the corrector.
Any other questions? If that's not the case, then we have a coffee break and continue at 10:15. So thank you once again.
So.